Good morning, welcome to new lecture. Today I will talk about internal forces. So today's topic is internal forces. If we have, for example, one beam in 2 dimensions and it is simply supported beam, assume one support, it is pin support, another one, it is roller support, and the length for this beam is L, and this beam is subjected to different forces. If I cut the part of the beam, for example, I cut this beam in the distance of x from point A, and I show the free body diagram for this beam. Now, this part of the beam will not be in equilibrium. It can move in the x direction, it can move in the y direction, or it can rotate. So, in order to satisfy equilibrium, I need to apply internal forces in cut point. At cut point, we will have 3 internal forces. One, we call it axial force or normal force. It will create compression or tension. They show with M, and always it will be in the member direction. You see, axial force, it will create compression or tension, and it will be along the member. This axial force will prevent to move in horizontal direction, so it prevents any motion in horizontal direction. We will have another force. This is axial force or normal force. We will have another force which is perpendicular to the member. We show that with V, and they call it shear force. Shear force prevents to move this part of structure or beam in vertical direction. We will have another internal force. We show with M, and they call it bending moment. This bending moment prevents to rotate this part of the beam. So if this part of the beam, it is not able to move in the x direction, y direction, and rotate, so it will be in equilibrium. So at cut point, for any structural member in 2 dimensions, we will have 3 internal forces. One of them, it is axial force, which is in the member direction. Another one, it is shear force, it is perpendicular to the member. Another one, it is bending moment. But if the structural member, it is in 3D space, in that case, if I cut the part of the beam, assume this is my cut point, and in 3 dimensions I have x direction, y direction, z direction. Internal forces in 3D space, 3 dimension, will be one axial force. Again, this axial force will prevent to move in the y direction. We will have 2 shear force, one parallel to the x, another parallel to the z. So we will have one axial force which is parallel to the y direction, 2 shear forces. They are perpendicular to the member. One of them, it is parallel to the x, another to the z direction. We will have 3 moments. 2 of them are bending moment. One of them, it bends member respect to x-axis. Another one, it bends member respect to the z-axis. So this is mx. This is mz, and I will have one torque, another type of the moment. They show with T usually, because it creates torsion in the member. So I will have three moments. Two of them, they are bending moment because they try to bend the member. One of them, it is torque because it creates torsion in the member. And I will have two shear forces and one axial force. So in 3 dimension, internal forces in each cut point or in each section, we will have 6 internal forces: axial force, shear force, bending moment, and torque. But for 2 dimension, I will need only 3 internal forces. In 2 dimension, we will have axial force, shear force, and bending moment. Only 3 internal forces. In real life, most structure, they are in 3 dimension, but fortunately the behavior, it is in 2 dimension, or we can simplify to the 2-dimensional behavior. So most of the time we will deal with these 3 internal forces, but in some space structure you need all internal forces in space. In that case we will have axial force, 2 shear force, 2 bending moment, and 1 torque. So altogether we will have 6 internal forces. For 2D space in plane structure, only 3 internal forces are enough to satisfy equilibrium. Let's now look at the positive direction of these internal forces. Depending on the textbook, you can see different positive direction, but in most textbook, if you have a beam, for example, it is simply supported beam, and this is left side of the beam, this is right side of the beam. If you move from left to the right side and you cut and you take the left segment, left portion like this, this is point A. I cut in the X distance and I want to see internal forces direction, positive forces direction whenever I take the left side. In that case, axial force in this direction it is positive. You see it creates tension in the member, it pulls the member. Shear force in this direction it is positive, and bending moment it is positive in this direction. If you take the left side, if you take to right side, this is left side. If you look at to the right side, positive direction, it is different. For example, point B, and you take right side. In that case, positive direction for internal force, axial force, it will create again tension. In this direction it is positive. Shear force, this time upward is positive. Bending moment, this time it is clockwise positive, but here counterclockwise positive. In order to remember, let's do like this. Let's cut a segment of the beam. You see this shadow part. I drove that part bigger. This is, for example, section B, section A, section A, section B. In section B, these are positive direction. Axial force, shear force, bending moment. In the section AA, positive direction, axial force, shear force, bending moment. You see, if I show one by one, axial force is positive always if it creates tension in the member. So this is positive direction of the axial force. Shear force, if you look at to that segment again, it is positive if the shear force direction rotate this segment respect to the center of segment clockwise direction. You see, this is upward, this is downward, so they will rotate this rectangular segment clockwise. So this is positive direction. Bending moment, it is positive if they bend beam like this. If you apply bending moment in this direction, it is positive. The form shape of that segment, if we apply bending moment in that direction, it will be like this. You can visualize that. So the form shape, you will see, you will have elongation in the bottom of the beam in extreme fiber, and you will have contraction in top fiber. So underneath of the beam you will have tension, top side of the beam you will have compression. If bending moment create tension underneath of the beam and compression in the top side of the beam, we call that it is positive internal bending moment. That is positive internal bending moment. You should learn this positive direction. You should practice and learn it. It is very important. Later on you will see why. Let's now look at a very simple example. Simply supported beam subjected to concentrated load at midspan, and find internal forces and show the variation of internal forces along the beam. Variation of internal force along the beam, we will call it diagram. For example, if we show the variation of shear force, we will call it shear force diagram. If we show the bending moment variation along the beam, we will call it bending moment diagram. For example, we have simply supported beam. This simply supported beam is subjected to concentrated load P at midspan, and the length for this beam it is L, point A, point B, point C. If I want to show internal forces in one section, which is in the x1 distance from point A, I can draw free body diagram. So free body diagram, point A, this is x1 distance. Now I cut it in the x1 in order to have equilibrium or to satisfy equilibrium in free body diagram 1, I have to apply internal forces. Internal force, the axial force in the section which is x1 distance from point A, and x1, this is Vx1 and this is Mx1. Pay attention, here x1 can have any value, but it should be between 0. 0 means you are cutting exactly at support up to L over 2, just before the P. So x1 variation will be between 0 to L over 2. In that case, if we look at to this free body diagram and we want to find these internal forces magnitude, we can find it. Why? Because here first we should find the support traction. We can find support traction if we apply P at midspan. Support traction will be P over 2 and P over 2. So here support traction, it is P over 2. This support traction is 0. and this is 0. If you remember, I found that using equilibrium equations, we can find support reaction. This is very simple, so I don't write the equilibrium equations. Now, in order to find nx1, I can write summation of forces in the x direction equal to 0 for this free body diagram. Here, I will have nx1 is equal to 0. In order to find shear force, I can write summation of forces in vertical direction equal to 0. So I can write P over 2 minus Vx1 is equal to 0. From here, Vx1 will be equal to P over 2. In order to find mx1, I can take moment respect to point O1 cut point. So if I take moment respect to point O1 cut point and put equal to 0, I will have mx1 minus P over 2, this force times distance, x1 is equal to 0. From here, I can find mx1 is equal to P over 2x1. So I found in this free body diagram the axial force equal to 0, shear force P over 2, and bending moment P over 2 times x1. Because I don't have enough space, only I will write final result here. So I will remove those. I will write nx1 equal to 0, vx1 equal to P over 2, and mx1 is equal to P over 2 times x1. Now if I cut this beam in another section, in section x2, after the load, so x2 will varies this time from from L2 to L. X2 after the load, so it will varies from L over 2 to L. If I show the free body diagram for the beam, here you will have reaction P over 2. This is 0. The cut point, it is x2. You have here external load P, and from here to here it is L over 2. Now if I show the internal forces in this section, I will have nx2, I will have vx2, and I will have mx2. Let's find these internal forces using equilibrium equation again. Summation of forces in horizontal direction equal to 0, I will have nx2 is equal to 0. Summation of forces in vertical direction equal to 0, that means P over 2 minus P minus Vx2 is equal to 0. From here, Vx2 will be equal to negative P over 2. If I take moment respect to cut point, point O2, and put equal to 0, I will have mx2 minus P over 2 times distance, so P over 2 times x2, because distance it is x2, plus P times distance from here to here. Entire this distance it is x2, this distance it is L over 2, so under the load up to cut point will be equal to x2 minus L over 2. So P times distance respect to point O2 will be P times x2 minus L over 2 is equal to 0. From here you can write, I can write mx2 is equal to P over 2 x2 minus P times x2 minus L over 2. Now, let's draw a variation of this function along the beam. This line I will show an axial force. Axial force means N. In the region of from 0 to L over 2, it is Nx1, it is 0. In the region or domain of L over 2 to L, we show it Nx2 and again it is 0. So entire beam axial force, it is 0. Shear force from 0 to L over 2, in this domain it is P over 2. So if I move up P over 2 up to here, underneath of the load it is P over 2 and it is positive. After the load, it means in the domain of L over 2 to L, it is Vx2, it is negative P over 2. So after this, it will remain constant and it will be the negative P over 2. Now, bending moment. Bending moment, so this was shear force V. Bending moment I show here, M. In the beginning, at x1 equal to the 0, it means point A here. P2 times x1, if instead of x1 I plug 0, it will be 0. So at the beginning it is 0. And this function, it is linear function. So if I increase the x1, mx1 linearly will increase. x1 can vary from 0 to L over 2. At L over 2, if I plug instead of x1, L over 2, mx1 will be P over 2 times L over 2. So it will be P L over 4. At x2 equal to the L at point B, here you will plug L. In that case, this will be P over 2 times L. This will be negative P times L minus L over 2. You will get again 0. And again, function is linear and it is positive. This will be axial force diagram, shear force diagram, bending moment diagram. I drove using classical way, using free body diagram. You can practice and draw a little bit faster, but in the exam you should follow these steps, you should show it. But there is another method. Let's practice from beginning. First I will find the reactions. Then, for example, for shear force diagram V, I will draw one horizontal line. I will move in the beams from left to right. At point A, what is the reaction? P over 2 upward. I will move from reference line P over 2 up. There is no force from A to C, so I will continue. At C there is force P down. From here, this point, I will move P down, so I will reach this point. There is no force from C to B. From C to B I will move. I have P over 2 up. I will move P over 2 up. I will close the diagram. This is positive, this is negative, this will be shear force diagram. Bending moment diagram. Bending moment here, it should be equal to the 0 because it is hinge. Hinge means no resistance against the bending moment. Here we can have rotation freely. So no resistance against bending moment. That means bending moment at hinge always is 0. If we apply concentrated moment, it will be equal to the concentrated moment. If there is no any concentrated moment at hinge, always and always bending moment at hinge should be 0. Now I move from A to C. Just before C, if you cut the beam, what is the moment here? P over 2 times distance L over 2. P over 2 times L over 2, it will be PL over 4. And because there is no force here, it will be linear. From C to B, again, there is no force, variation will be linear. At point B, because it is hinged, bending moment should be 0. Why it is positive? Here using free body diagram, you see the answer is positive. But if you don't draw free body diagram, look at the deformation of the beam. If you apply load, this beam will deform like this in reality. It will move down. We will have deflection or sagging. So underneath of the beam we will have elongation. That means tension underneath of the beam. Tension underneath of the beam, it means positive bending moment. So the bending moment is positive. Okay. For next session, try to draw bending moment for these beams, and I will draw two and you can compare. This is your homework. This beam, simply supported beam, subjected to two concentrated load, and each one in L over 3. So we have simply supported beam subjected to concentrated load. Each part it is L over 3, A, B, C, D. Find the internal forces in AC segment, BC, CD segment, DB segment, and draw shear force diagram and bending moment diagram and axial force diagram for this beam. Next one, draw internal forces diagram for this beam. Simply supported beam, length is L, subjected to concentrated moment at mid-span at L over 2. Next one, this beam, simply supported beam, subjected to distributed load, uniform distributed load. The intensity of the load, it is lowercase w pound per feet, and the length is L. Find internal forces and draw axial force diagram, shear force diagram, and bending moment diagram. So 1, 2, 3, and let's I add one more. These are your homework problem. You have simply supported beam subjected to concentrated moment here at support A, and the length is L. Draw shear, axial force, shear force, bending moment diagram for this beam. Next one, it is cantilever beam subjected to concentrated load at free end. The length is L. Draw internal force diagram for this beam, A, B, and the last one, it is cantilever beam subjected to uniform distributed load. The intensity of the load, it is lowercase w pound per feet. The length is L, A, B. Draw internal force diagram for this beam. So for all these examples, it is your homework problem. You will draw internal force diagram. You will show the variation of internal forces along the beam. Internal forces, because all of them, they are in plane beam. So internal force means variation of axial force, shear force, bending moment. It means axial force, shear force, bending moment diagram you will draw for these beams. One of them simply supported, subjected to two concentrated load and each one at L/3. Another simply supported, subjected to bending moment at midspan. Another simply supported is subjected to uniform distributed load. Another simply supported, subjected to concentrated moment at point A at this support. The next one, it is cantilever. Cantilever beam means one end is fixed, another end is free. Is subjected to concentrated load at free end. Another one, it is cantilever beam subjected to uniform distributed load. So try to do it, and in next session I will do it. You will compare your solution. Thank you so much for watching this lecture. See you next session. Bye.